So I'm going to talk today about how to make a moving boat measurement and how to do that with an ADCP. Feel free to interrupt me. Let me know if you can't hear me on the microphone or if I just need to talk louder. Don't feel like you need to just wait until the end to ask a question. Feel free to interrupt. So I'm going to start out with a little bit of a brief background on SonTek, and then I'll go into some definitions. So I'll talk about what acoustic Doppler technology is, and then I'll also define what a discharge measurement is. Then I'll talk about site selection, because that's very important for when you go out to go make a measurement. Then I'll actually talk about the specific instrument that I'm going to be making a measurement with. I've got it on display up here on the boat. It's our Sontek RS5, and then I've also got one here that I can pass around a little bit later. So after I kind of go over just the nuts and bolts of what's in an RS5 and what you'd actually be taking out to the field, we'll go over just the very basics of how do you make a flow measurement, what are the best practices, some real-time evaluation that you can look at, and then I'll go through a simulated measurement as if we had this on the river, and we'll just use our imagination. So I'll start out with that brief history of SonTek. So SonTek was founded in San Diego in 1992. We are the original creators of the acoustic Doppler velocity meter. So I'm not going to be able to point to this, so let's see here. Let's see how this works. Maybe I can. Can you see that? No. All right. So this ADV up in the upper left-hand corner, that's like the very first ADV that we came out with. It has a really small sample volume, was really designed for lab applications initially, then eventually used out in the ocean. But everything there that you see is required, so like that big card. And so it was kind of a bit cumbersome to use. And so over the years, we've worked on developing more compact instruments. And so now we manufacture instruments that can be deployed in the field. So they're waterproof, right? You can't imagine taking out that card to the field. And we've really kind of transitioned from manufacturing in the lab segment and the coastal segment into more of a surface water hydrology company. So this is a timeline of our instruments here, and you can see all of the initial instruments we were creating were really for ocean coastal, and then there was a shift sort of in 2000, 2001, where we started to design instruments that be taken out to the field to collect a discharge measurement or for continuous monitoring if you needed to have some real-time data out at your site. So our instruments can be used out in a variety of different environments. I like to use this picture because I kind of imagine I'm standing on a bluff and looking out, and I can see all of these different types of environments where all of our different instruments can be used. So in the upper left corner, you'll see some bathymetry mapping that could be done with our acoustic Doppler instrument, the SonTek M9. And then down in the sort of left corner of this picture, you have what looks like a really nice canal. That's somewhere that you could put one of our bottom-mounted acoustic Dopplers for continuous monitoring. And then in that canal, you might be able to wade out, walk out, and collect a discharge measurement with our flow tracker. That's our wading ADV. And then if you get into the sort of shallower, what looks like marshy area in the bottom right-hand corner, that's where you can take out our newest ADCP that would be designed for shallow water flow, and it could be used for mapping velocities, but also for discharge as well. If you sort of look towards the back, look at that larger river in the back, that's where you might find one of our SonTek SLs installed for monitoring velocity and depth. The SLs are often good predictors for developing rating curves for monitoring for flood conditions. And then beyond our acoustic Doppler instruments, we have an entire suite of water quality instruments from our YSI brand. So we've got pro samplers, multi-parameter sondes. We've also got water level sensors like the bubbler. And so we offer lots of solutions to all of your environmental needs. And then beyond sort of the typical surface water environments, we can also use our instruments in stormwater and wastewater applications. So I mentioned the IQ before. This could be used in an effluent situation. And then flow tracker can actually be used in manholes because we have these extension cables that allow you to deploy the ADV that's making the measurement down into the manhole and then actually control it from the top side. So those are sort of just the different places you might come across our instruments. And now I'm going to go into the actual acoustic Doppler theory behind our instruments. So I like to think of this in a twofold definition. So we have the hardware, and then we have the actual theory or physics behind the Doppler technology. So I'll start with the hardware. So we've got transducers in all of our instruments. They come in all different shapes and sizes, but essentially they are what you see in the upper left-hand corner. It's a ceramic surrounded by epoxy, and that's placed inside the actual instrument. And so this is just essentially like a little speaker, and so it's putting out a pulse, a sound pulse, and it might also be listening for that sound pulse. And you can see that they, while inside it's just this ceramic, the transducers come in, like I said, all different shapes and sizes, much larger for lower frequency, and then much smaller when we get into really high frequency pulses. So how do these transducers operate? They operate under either two conditions, either a monostatic or a bistatic. And Sontek started with that ADV, and an ADV is a bistatic acoustic Doppler. So that means that we have a center transducer. I'm talking about the one on the right here. So we have a center transducer that's sending out an acoustic pulse at a known frequency. And then we have our receiver arms on the outside. Those receiver arms are listening, and they're looking into a very small sample volume indicated by that cylinder there. And so in this case, we have dedicated receiver transducers and transmit transducers. So they have different jobs. And we need both of those, two of them, to resolve what's happening. For a monostatic instrument, which is the rest of the instruments that we manufacture, and this is what the RS5 is, and that's what I'll be really talking about today. The same transducer that sends the signal is also listening for the signal. So that little speaker inside that ceramic is sending out a pulse, and then it's also a microphone listening. And so for a monostatic, our sample volume looks very different. So we actually have several sample volumes, and they go out along each of the beams. So that's what I'm trying to show with the beams, the lines that are coming out of each of the beams from the RS5 there in the middle. And right now, our only ADV that we have is the flow tracker, which can also be used for a discharge measurement. So looking at the monostatic in a little bit more detail, so we have our center transducer, if you're looking on the right-hand side. We have our one transducer that we're just thinking about. It's sending out a signal into the water. That signal is then ricocheting and reflecting off of particles that are in the water. And that sound pulse is going in all different directions. And one of those directions will be back to that transducer that sent the pulse. So we're sending out a pulse. That pulse is reflecting off of particles. Some of those reflections are coming back to that same beam that sent the pulse. So it's really just that simple. If we think about this from an actual instrument that's facing down, that means this is happening on all four of these beams. And so they all four have a sample volume. Okay, so that's just the transducers. We've just talked about the hardware here. So now we'll get into the actual physics, which is the Doppler shift. So the best way to think about the Doppler shift is to imagine that you hear, you're standing on the sidewalk or you're sitting in your car, and you hear a car go by with some really loud music playing. As that car approaches you, and as it is right next to you, and as it leaves you, the pitch in that music is going to change. And in fact, if you were to just close your eyes and listen, you could tell that it's approaching you and that it's leaving you. And you wouldn't see it, but you can tell that just simply by the change in pitch that's happening. So that change in pitch is the Doppler effect. So because something is moving and we are hearing that car or that stereo move past us, we're hearing a change in the pitch or a change in the frequency. So we're going to use that and we're going to apply that to our technology. So when we think about Dopplers, we have our transducer here. It's sending out that acoustic pulse at a known frequency. It's then listening for a return from that along that same beam path. And if the water is moving past it, then we should hear a change in frequency because the water has moved past the transducer, just like we would hear a change in frequency as a car drives past us, and that noise changes in frequency simply because of the motion. So if you were to imagine sitting there in your car, somebody comes up next to you and they just start blaring their music, you don't hear any change in frequency because there's no movement happening. So it's dependent on the movement. That's a critical aspect of acoustic Doppler theory. So the pulse, the sound pulse is being sent out. It's reflecting off of material in the water. It's coming back. We're listening for a frequency change that happens because the water is moving past. So that frequency change, we're just making that conversion right along the beam path. We need to be able to convert this frequency change to something characteristic about the water. We need to convert this to a water velocity. That's what we're after, right? So in order to do that, we have to know how the water moves through, how the pulse moves through the water. And that's dependent on the physical characteristics of the water. So that's going to be our salinity and our temperature. So that's why speed of sound is really critical for acoustic Doppler instruments. Anytime you have a Doppler instrument, you're always going to have a temperature sensor on board to give you real-time temperature corrections. And then there's always going to be a way for you to enter a salinity value. And we have this really handy tool. It's pictured on the right, this Castaway. It's the little orange, looks like a really large pill. I wouldn't want to try and swallow it. But so it fits in the size of, fits in your hand. It's a little CTD. You can cast it, pull it back up, and then you'll get a sound speed profile. It downloads directly to your PC, and then you have your sound speed correction if you need it. Now, in a lot of freshwater rivers where you're measuring discharge, you have well-mixed bodies of water. So you're not necessarily worried about making a correction, but you do want to make sure you're entering a correct salinity value if you do have any salinity. If you're in freshwater, it's pretty easy. It's going to be 0. But we offer you this ability to make the correction if it's needed. And this is definitely a lot more important in coastal areas or just in high saline environments. So if you're measuring anywhere near the Great Salt Lake and you have any runoff from that, you need to get a salinity value. Okay, so to recap here, because I've thrown a lot of tech at you. So we have our transducers, and they are sending out an acoustic pulse at a known frequency. They're then listening for a change in frequency along that beam path. They're using that change in frequency along with the speed of sound to then convert to along beam velocities. And then we are going to take our along beam velocities and we convert them to XYZ using the known configuration of the geometry of the beams. And this will be different for every instrument. Every instrument goes through calibration at our factory. We measure exactly what angle all of these beams are at, and then we use that to convert from our raw beam velocities into our XYZ velocities. And then if we have a compass on board, then we can convert that to ENU velocities, which is Earth velocities, so that's east, north, and up. And that's what we'll be doing with the RS5, because that's being used on a boat that's going to move around. So this graphic that I just put up here is just showing you that raw signal that gets sent out from the beams. Then you have your raw beam velocities in that center plot. And then on the right-hand side, we've converted it to our Cartesian XY velocities. So there's a couple assumptions that go into using an acoustic Doppler, and that is spatial homogeneity and particle velocity. So for spatial homogeneity, what I'm talking about is that all 4 of these beams need to be seeing the same conditions. So I have one beam that's pointed this way, I've got another beam that's pointed this way, and then I've got another pair pointed, so they're all pointing in 4 different directions. All 4 of those beams need to see the same flow conditions. That is critical for actually resolving out the correct downstream velocity. So you don't want one beam pointing into an eddy and the others not. You also don't want all of them pointing into an eddy. So that's a critical piece about using acoustic Dopplers, and it's why I'm going to take some time to talk about site selection. The other big assumption we make is that the particles in the water that we are sending that pulse out to and reflecting off of, we're assuming that those are moving at the same speed as the water. So we're not actually measuring the water, we're measuring the particles that are moving along at the same speed as the water. Okay, so talked about acoustic Doppler technology. Hopefully everybody has a good handle on what exactly an acoustic Doppler is. Now I'll just quickly define what discharge is, and then I'll get into site selection. So discharge is very simply, in definition terms, the volume of water moving down a river per unit time. And it is often referred to as flow or Q, discharge, flow, Q. All 3 of those get used interchangeably. So if I mention flow later, I'm also talking about discharge. And that is essentially just the cross-sectional area times the mean channel velocity. This graphic here on the right is taken from the USGS. This is just their kind of way to define how they measure discharge. You're basically measuring the area in a panel, so you have your width and your depth. You get the velocity in that panel. That gives you a discharge for each panel, and then you add that up to get your total Q across the entire cross-section. For a moving boat, we're not actually dividing up into these very discrete sections. Instead, we're doing what you see on the bottom, which is we're moving the boat in one single motion, and we are collecting several of these panels so small that you can't even really see them. They're 1 second each. So it's really just an integral of the area and the velocity. And so in many cases, you can go out, you can take your ADCP, you can collect your discharge data, you can leave a staff gauge out there and build a rating curve so that you can start to predict what your discharge will be based on your rating curve. However, there are many situations out there where your channel just doesn't have uniform conditions. And so there's a lot of situations where you actually have hysteresis, which just means that your falling and your rising limb on your flood are not equal. And so that means that one stage doesn't necessarily, it could equal 2 different discharge values. So that's when building in another instrument, like one of our fixed systems for velocity measurement, becomes an option for you. When you don't have a good relationship between stage and discharge, and you need to actually build in a velocity relationship between your stage and discharge. That's when we can get a little complicated. We bring in one of these instantaneous ADCPs, and then we pair it with one of our continuous monitoring instruments. And I'm showing here the SL in the bottom left. And then in that center image, we've actually got an SL deployed, and somebody's out there collecting a discharge measurement to help build that rating curve. All right, so I am going to take a little bit of time to talk about site selection, because even if you have the most accurate instrument out there, if you choose a bad site, it's garbage in, garbage out. So for example, you would not want to pick the site on the left. While that's beautiful, it's not a good place to make an ADCP measurement. There's a lot of turbulence, there's a lot of different inputs here, and so there's nowhere in that picture where I see sort of all the conditions and the criteria you want for a good measurement. The site here on the right looks like it has really nice laminar flow. There is a bit of a control structure downstream. But this is a known site that we measure at a lot, and there's nothing upstream for a really long time, so we know that there's nothing actually impacting where we're making our measurement. Okay, so picking a good site is just going to help with your data quality. So when you're trying to decide on where to install a gauge station or where to go out and make a discharge measurement, there's several different criteria you want to look at. And in an ideal world, you'd be able to cross all of these things off the list, but we know that that's not always possible. So as much information as you can gather about the site, if at all possible, try and do a trial installation. That's not always possible, but if you can, it's the best way to know if it's going to work out long term. Go collect a discharge measurement. Go grab your ADCP and actually make some discharge measurements. Look at the data, look at the structure of the velocity. Make some measurements along the reach, not just in one spot. If you can, run some surveys, whether that's just getting depth, or if you're actually running an ADCP survey, you could get your velocity data mapped. And then photographs, if you can find any kind of historical photographs, that will give you an idea of what possibly has changed over the years, what might happen in the future. And then it's also important to understand what are your hydraulic requirements, also what your instrument specifications are to see if you're even going to be able to meet those needs. And then you also want to think about maintenance and how often you're going to need to get out there, what's feasible, what's safe. So there's a lot of things to think about when you're deciding on an actual station for making a measurement. So these are sort of the ideal criteria that you'd want. This is sort of your kind of perfect station where you've got your uniform velocity profile. You see that all those arrows are pointed directly downstream, perpendicular to the tag line. You've got a nice straight section here. And so you sort of meet all of these criteria that we list out. You've got your steady flow conditions. You've got your uniform velocity distribution over the cross section. It's a nice straight reach. Our rule of thumb is that you should not install an instrument unless you have 5 to 10 channel widths of straight section. And that goes for just making a discharge measurement as well. And if you can meet that criteria, that 5 to 10 channel widths up and downstream, that tends to check all of these other boxes. But we know that it's not always possible to do that, so you kind of just have to make the best of what you can. And you just want to try and check as many of these boxes as possible. So other things you want to think about, which I just mentioned earlier, are being able to access the site at all different stages, making sure that that's safe. And then also making sure that you have a stable cross-section. Our instruments are going to rely on being able to measure the area, and if the area is changing a lot, that could be problematic for a long-term gauging station. So those are all the things you want to check off. These are the things you don't want to check off. So you want to avoid these things that I'm showing here. So any kind of control, bend, or steep slope, you don't want that in your measurement section or really anywhere near it. You also want to avoid obstructions and excessive plant growth. Sometimes you're going to have to go out and clean your channel to make a measurement. That is just going to be a part of the job sometimes. You want to make sure that you're avoiding turbulent flow or negative flow areas. You also want to avoid scattering conditions because that's going to impact your cross-sectional area. You also want to think about potential for vandalism. People and animals. Animals will chew cables and all sorts of stuff. They get very curious. And then for making a discharge measurement, like we're going to go over here, we want to avoid large ferrous materials. So really large bridges that have just a ton of rebar in them. That can cause problems. There are ways to overcome it, but if you can avoid it, avoid it. We do have some really handy tools built into our software. You can actually detect if you are getting too close to something that is creating a magnetic field. So we actually have a magnetic error plot. And so the red X's in the middle of the time series here are showing that we've gotten too close to something that we are now measuring the magnetic field of that we did not measure during our compass calibration. So we do have these tools built in for you, and I'll go over more of these real-time evaluation tools later on when we go through the measurement process.
What is a scattering condition?
A scattering condition would be if you had really swift velocities on a bank that's curved, you'd probably be like cutting out the outer bank. Like that's a sort of simple example. Okay, so we'll talk about our site selection here. So I'd like to kind of make this a little interactive if possible. So we've got a couple sites that we'll propose. And all we've been given is this satellite imagery and a little bit of information about the different sites that we have options for, and then the length, or sorry, we know what the channel width is because we can measure that on the imagery. And then we can figure out, okay, what's 10 channel widths in distance downstream. So does anybody want to volunteer to rule out any of these sites for an ADCP measurement? 5 and 2. 5 and 2. Okay. Yes. So 5. Yeah, 5 is right on that bend, so that's no good. And same with 2. That's also right on a bend, so that's great. We don't want to use those. So we've got 1, 3, and 4 left.
Is the optimal one?
Which one do you want to throw out? Or you can guess on the optimal one if you want.
3. It's unknown on 1.
Yeah, exactly. Yeah, so you said you'd throw out 3? Yeah, okay. Yeah, so we've got a little bit of what looks like maybe a tributary coming in there. It's also on a slight bend for site 3. And then we don't know what is downstream of site 1. So that looks like a good approach, but we don't know what's downstream. So that leaves us with site 4, which looks like a pretty nice straight section. So now we'll head out to the field and we'll look at the site and decide where along that reach that we're going to choose. So now we've gone out there and we've realized that there's a couple options here. We've got this one site that we could put upstream of this really big cobble boulder thing. We've got an option to go right across from this large boulder. And then we have also got an option to set up below and downstream of that. So where do we think, or what should we rule out at this point? Okay, so we're going to rule out 3. That seems like a good idea because there's probably an eddy right downstream of that large boulder there. What else do we want to throw out?
Probably 2 because it would see increased velocity because of the narrowing of the channel.
Yeah, exactly. Yeah, so we're pinching in the velocity there as the channel narrows, and so our uniform velocity profile that we're looking for doesn't exist there. So it looks like Site 1 looks like a good choice. And we've already figured out that this whole reach looks pretty good in general. So I'd be pretty satisfied with Site 1. Let's try and make our discharge measurement there. And then just pointing out the issues with the other sites there. So we've got the skewed flow, and then we've got the backflow and turbulence in the other areas. So sometimes when you go out to a site, it looks nice, or you have a general idea, or maybe for reasons like ease of installation, you think you know where you want to install your instrument. So if you have the ability to take an ADCP out and map an area, you're going to pick a better spot if you have the ability. So the image I'm showing here, we took one of our ADCPs out, and the sort of zigzag lines, that's the boat track. So we drove around. The original idea was to install an instrument on the bridge because that was the easiest thing to do. So somebody went out, collected this survey with our M9, and we were able to go and map the velocities. That's what all the tick marks are that are coming off of those boat tracks. And so by doing this, we then loaded those data into our software. We interpolated the velocity so that it was a little bit easier to look at in a grid form. And we ultimately decided that the bridge was a terrible place to put the installation because there's this huge eddy forming at the bridge piling. And that's not going to be a good place for an instrument installation. So we actually ended up recommending that we install further downstream from the bridge where we could see the really nice uniform velocity section. And that's just going to lead to better data in the long term. All right. So I've gone over acoustic Doppler technology, how to select a good site. And so now I'm going to take a little bit of time to talk about exactly what the RS5 is so that you can get an idea of how this would be used out on the water, and then we'll go through that process. So actually, I'll pass this around. So the Sontek RS5, what is it? It's a very portable ADCP, which is an acoustic Doppler current profiler. We're passing it around right now. It's designed to be small and portable. It's just a pound. And it can be set up on this boat in minutes. And it's designed to be really easy to use. It's got a modern software. It's got plug-and-play GPS, which I've got connected here. And then we've got an option for network RTK, which is a new feature and can be really handy if setting up a base station, which we have set up over there, is not an option. So what you're holding in your hand, what's being passed around, like that's it. All of the electronics are in there. There's a battery that goes inside. If you wanted to connect GPS, you just have a GPS connector coming out. It would connect to, we have the green antenna on top of the RS5 right there is our RTK GPS. But it's just all the actual ADCP and everything you need to make a discharge measurement is included in that small portable device. We're using Bluetooth for our communication with the PC, and our batteries are just lithium-ion rechargeable. And so if you're at all familiar with our other ADCPs that we offer, we have the River Surveyor M9 and S5. That requires this PCM box, which is pictured at the upper right corner. And that's actually, that's not needed with the RS5 because everything is included in that system right there. Okay, so we have a couple different options. You can just purchase this as just the ADCP. You have bottom tracking enabled so that you can keep track of where you're moving along the transect and your speed over ground. So you're able to calculate the water speed, your area, and calculate discharge. That's a great solution for small canals where you don't anticipate any kind of moving bed. And sort of what we're showing you here is what you get in the case, and then you can, away you go on your discharge measurement. We've got a couple different floating platforms for you to install this on. And so in the next couple slides, you'll see two photos always. One is going to show you on the hydroboard micro, and then we also offer a torrent board micro that can be easily upgraded to a remote boat. So it kind of just depends on like where you think you'd go. If you need a remote situation in the future, we'd recommend the torrent board. The micro board is a great solution to just get you out there on a tethered banker operated cableway. If you need GPS, we do offer that. We offer actually two different GPS options. The first is differential. So it comes with this geode. We've got a slightly newer version now, but this is a plug and play. You can connect to it through the geode app. It's an off-the-shelf piece, so it's meant to be very easy for you to integrate. And that's going to give you a differential solution. It's about 1 meter accuracy for your position data. And that'll be good for really wide streams where you need georeference data. We also offer our Sontek RTK solution, which is what I have installed on the board here. So in that case, you're actually going to get two GPS receivers. So you have one that roves around on the boat with the ADCP, and then you have another one that gets set up on a base station, just like we have here, set up on a tripod, and that base station is then sending corrections to your roving GPS on the boat. This type of solution will get you centimeter accuracy. So if you're working in narrower channels where you need georeference data or you need to overcome a moving bed, RTK is going to be a good solution for you. Also, if you plan on doing any kind of mapping, so if we aren't talking about discharge data, we're talking about velocity mapping or bathymetry, that's when you want the accuracy of the RTK GPS. Let's see. So in this setup here, we are running the GPS off of that same battery that's inside of the RS5, and then we're using that same type of battery to run our base station. So same batteries are used with everything. The radio that I plug into my PC is the same radio that you see sticking out of the top of the boat. Everything is interchangeable to try and make it a little bit easier for the users. The other thing I wanted to talk about with RTK is that you don't necessarily have to set up the base station. If you have a network RTK where you're doing work, and there are actually a lot of free services out there, a lot of states have set up services. You can log into that actually. You just need to have the rover part. In our software, you would log into the network RTK with like the IP address, your login information, and then as long as you have cell service, you can get those corrections feeding into your rover instead of setting up a base station. So that's really helpful if you can't maintain line of sight between your base station and your rover. Okay, so those are the three different options for the RS5. I'll quickly mention that we do have other river surveyor systems in our family. We have the S5 that is discontinued. The RS5 has replaced it, but there are still plenty of them out there and in use. We also have the River Surveyor M9, which has 9 beams, 9 transducers, and it has 3 frequencies. And then, of course, the newest one that I'm talking about today is our RS5. So these are designed for sort of different depth environments. The RS5 maxes out at 6 meters. So if you're working in rivers that are deeper than that, it's obviously not going to be an option. That's when you would look at our River Surveyor M9 as an option for a discharge measurement. So this is just showing you a couple different deployments of the M9. This would be your choice in really high sediment load measurements. So in those flood conditions where you need to go make a flood measurement, when you have a lot of sediment, it's hard for the higher frequency, I don't have it here anymore, the higher frequency beams on the RS5 to penetrate. So the M9 has lower frequency beams. It can penetrate through high sediment and actually get you the flood data that you need. So I mentioned earlier about the PCM. So this is what I was talking about. If you have our M9 or our S5, you'll have this PCM, which is supplying the power and the telemetry back to your PC. And then similarly, just like with the RS5, if you have the RTK solution, you'd have a tripod set up with our base station set up on the tripod. And in that case, you would have a separate PCM for your base station with the M9. RS5 has much less components. You'll see there isn't any box hanging off the side of the tripod here. That's because we've got the battery up in the antenna and the radio is internal. So we're communicating between these two antennas with a radio that's internal. So it's not external. You don't have a bunch of cables hanging out. And so this is just an example data set from an M9 that shows the range of that system. So on the right-hand side here, there's a color plot, and you can see it goes from really shallow to much deeper depths. It actually goes beyond the profiling range of the velocity beams of the M9. But the M9 has this really low frequency echo sounder in the center, so we're able to get a depth measurement, and then we just extrapolate that section that we're not measuring in. And then finally, we've got the RS5 here. This is sort of your shallow mid-range ADCP. It can be used as shallow as 0.3 feet, which is really shallow. So it gets into your edges a little bit more, gets into those shallow sections. So you're just walking away with more measured data than you would be before. And then both of these ADCPs, the M9 and the RS5, they have what we call Smart Pulse, which I'll talk about on the next slide. But basically, they're using different pulse techniques to get you the best velocity data possible. And as I've talked about, we've got different GPS options. And with the RS5, we're running the RSQ software, which I'm going to show you later on when we simulate data collection. And in that software, we've really tried to keep all of the things that made sense in River Surveyor Live, which is what we use for the M9, but then we've tried to just make it a little bit more intuitive, which includes putting the moving boat section and the stationary section all into one software. So today I'm talking about a moving boat measurement, but there is a stationary measurement that you could make with this instrument, and that's all done within one software now. So Smart Pulse, I do want to take a little bit of time and talk about this because it's a huge feature of the RS5 and the M9. So when you're going out, especially if you're going to go out for a flood measurement, it's a race against the clock. and safety is number one. So you want an instrument that's going to work well and that you're going to be able to deploy quickly, and it's going to collect the best data possible. So Smart Pulse does that. Smart Pulse does the best data possible for you. So every single every single second, it sends out a few pings initially to figure out what cell size I should use, what frequency if it's the M9, and then what pulse type. And then it's choosing that for that particular sample. It's setting it up, and then it's sending out the pings for the measurement, and then moves on to the next second, and it does the same thing. And so as you move from shallow to deep, it's going to adjust the cell size for you. And so what this means, when we look up close at it, you actually see there's step changes in the beginning of the data collection, and that's because the instrument is selecting the blanking distance. So that's the space between the transducer face and where the measurement starts. So it's adjusting that. It's adjusting the cell size. You can see out in the channel, you can only see about 2.5 cells there because the cell size is so large. But then near the bank, the cell sizes get much smaller, so we're just fitting in a lot more cells into that shallower section. And again, it's doing this for you on the fly. You don't have to think about it. You don't have to know conditions of your channel ahead of time to try and pick any of these modes. It's selecting the best for you for each measurement, for each second of each measurement. And so what this translates to is really beautiful high-resolution data. So the top plot here are data from the RS5. These were collected all at the same exact transect at the same canal. And you'll see you can actually see the velocity structure in that top plot. You can also see it with the M9. We're using our Smart Pulse technology here. And then as you look at the other comparison plots, you'll notice that they look kind of like confetti a little bit. You don't really see the structure. You see a little bit of the high resolution data on that third plot on the edges. But if you wanted to understand what exactly was happening there for maybe a habitat study, you wouldn't get that picture unless you had the RS5 or the M9. When you average this all out, the discharge is going to come out the same. But if you want to understand something about your site a little bit more, the RS5 and the M9 are going to actually give you that information. Okay, great. So we're going to get into the flow measurement now. So we'll get into the actual procedure of how to make a moving boat measurement. So again, just to recap what we're trying to do, we're trying to get the cross-sectional area. And then as we're doing that, we're measuring the velocity. So a moving boat measurement is made up of basically the same components regardless of what instrument you're using. So you've got a cross-section, it's defined. And then you've got a start edge where you're going to start your measurement. You've got your middle transect where you're going to be moving the instrument across. And then you've got your end edge. So those are just the very basic components of a flow measurement. So when we look at what data we'll have after that, we can see what portion of that is actually measured. So that means that we're doing a lot of extrapolation elsewhere. So we're extrapolating the bottom, the top, and those side portions. All right, so when we're collecting our edge data, we're going to position the boat as close to the edge of the channel as we possibly can. But we need to make sure that we have depth underneath of the instrument so that we can collect velocity data. So once we've figured out where the closest point to the edge for which we can still collect velocity data, then we'll say, okay, this is a good starting edge. So then we'll need to measure the distance from that edge of water to the ADCP so that we can tell it what that space was to interpolate. Oops. So once we've entered that into the software, we'll collect 10 samples at this edge so that we can use those 10 samples to extrapolate that section. Once we're done with collecting those 10 samples at the edge, we'll move into the transect. So for the transect portion, we'll just be moving the boat steadily across the transect. And we'll be doing this in a way so that our boat motion is as smooth as possible. So this is what it will look like as we move the ADCP across. We'll be collecting our velocity data underneath. And then when we get to the far edge, we will not drive our boat outside of the channel. We will stop at the channel. We'll stop at the end edge and collect 10 samples at the end edge. And then once we're done with those, we'll use that for interpolating the end edge. Okay, so just a quick recap. We've got our start edge. We'll collect our 10 samples there. We'll move across the transect, and then we'll collect our 10 samples at the ending transect. Just like for the starting transect, or for the starting edge, we had to enter a distance from the edge of water to the ADCP. We're going to have to do that for the end as well, so that we can properly extrapolate that section. So another way of looking at this, this is just another animation we have. So we're collecting our 10 samples, then we move across. This one just shows you a little bit more structure. It's not like that uniform cross-section here. All right. So the other way to make a measurement is a stationary measurement. And you might do this if you had significant moving bed at your site, or if you had trouble with your GPS, or if you had some compass issues. So I did want to mention, we do have the stationary discharge measurement, and that's available directly in the RSQ software. We also have this available with GPS. So if for some reason you can't string a tagline across and measure those distances in between each station, you can actually use your GPS for position. And this method is based off of the USGS midsection method. So that's taken directly from their SOP. And that comes from weighting measurements, where you do walk in, you have to read off of a tagline where you are, you read on a weighting rod the depth, and then you measure velocity. And so that's how the flow tracker is used for a discharge measurement. Okay, so best practices for actually collecting your discharge data. So there's sort of like a checklist you want to go through. So obviously you want to set up a tagline or a bank-operated cableway, something so that you can move the boat back and forth. You're going to assemble your instrument. You want to make sure you've got your communication is set up. Then you'll configure your instrument. So for the RS5, that means you walk through the RSQ software. And you need to do a compass calibration. Then you'd place it in the water. I try and place it in the water as quickly as I can to get the temperature sensor equilibrated with water temperature. And then I like to start the system pinging so I can just make sure everything's okay. And then that way I can check the GPS. Once I've done all that, then I'll actually move into the moving bed test. So I'm going to test for a moving bed, and then I'll go into my moving boat measurement, and I'll be looking at my QA/QC the whole time. So a compass calibration. The compass calibration at SonTek is known as the compass dance. So you'll pick up the boat. I'll show you. So you're actually going to pick this up, and you're going to make two rotations while pitching and rolling it like this. And it should be this painfully slow. because you want each of your rotations to last 1 full minute. And the pitch and the roll of the system is going to be dependent on the actual water surface conditions. So if you have a pretty calm surface, you're going to pitch and roll it pretty calmly. If it's a rough surface, then you'll be pitching it and rolling it a lot more like this. So you'd continue that. I'm going to speed up. You do that twice. And then you've got your compass cal. So again, 2 rotations. Each rotation should be 60 seconds. That ensures that you're going slow enough so that you're not tripping the accelerometers. If you don't have a tethered boat like this and you have it mounted to the side of a jet boat or a manned boat, you're going to actually drive that boat in a figure 8 to do your compass calibration. For a tethered boat like this, you'll be doing it on the bank, and you'll try and get as close to your transect as possible. You're trying to mimic the magnetic field that the boat is going to encounter during the measurement. So always keep that in mind. A moving bed test. So it is standard operating procedure to test for a moving bed. A moving bed is sediment that's moving along the bottom of the river, and that will directly impact the ADCP's ability to track where it is and properly track the velocity. So you need to know if there is one or not to know how you're going to make your measurement. So we have tools built into our software. We have a loop test and a stationary moving bed test. These come directly from the USGS. We're just using their operating procedure and implementing it in our software. So there's a couple of requirements for a loop test. You have to tow the boat in a loop. That's where that comes from. And you're going to start and stop at the exact same location. This does require really good boat operation. So you need to be able to bring the boat back to that starting position. And this entire test does need to last at a minimum of 3 minutes. So once you complete that, you'll get results on the software program. It'll tell you if there is one or not, or if it recommends if you should do the SMBA. Okay, so the other option for a moving bed test is the SMBA test. So this is a lot easier to do. You would hold the boat out in the deepest or fastest section of the water, and you would collect the SMBA test. One test is 5 minutes. So off the bat right there, you're already spending a lot more time collecting SMBA, but it doesn't require good boat operation. So if you're new to a moving boat measurement, this might be where you start. I'm kind of always asked the question, which one should I do? So I like to put a little time in here for that. If you do test positive for a moving bed, so you have one, if you did that with a stationary bed test, you would then need to repeat that 2 more times. So that means 15 minutes you're spending collecting a moving bed test. That's a lot of time, especially if you're short on time in the field. A loop is going to take you at least 3 minutes, and it's also going to give you a little bit of reconnaissance. So you're going to quickly make a measurement, essentially. You're going to go across and back, and you're going to get an idea of what you're going to be encountering during the measurement, what kind of velocities, if there's anything that's in the channel that you need to address before your measurement. And then the USGS actually has a very clear set of guidance over what track references and what to do if you encounter a moving bed. This is a very, very, very simplified decision tree on how to deal with a moving bed if you have one. But essentially, their rules for collecting a flow measurement are that you have an even number of transects. So again, a transect is going to be your start edge, your transect where you're moving the boat, and then your end edge. So you have to have an even number of these, and you have to be out on the water collecting your discharge measurement for at least 12 minutes. They call that an exposure time. So those are the requirements from the USGS that you need to test for a moving bed, and then you also need to have the even number of transects and a 12-minute exposure time. My personal tip is to just do the work and check the duration of your measurement. After you think you've gotten your measurement done, you can always add more transects afterwards. So while you're collecting data, there's going to be a lot of real-time feedback in the software. So first, you should always make sure you have your setup set correctly. But you're going to be getting information from the compass, the GPS. You'll know if you had a loop method or an SMBA in there. You'll have your edge data, and as you accumulate your edge data, you might see some QC warnings about that. And then same for your transect data. So in our software, we lay it out so that we have tabular data on the left, and then we have time series on the top, a sort of map plot in the middle, and then a color plot on the bottom. And this is our transect tab, and it's what you'll kind of be living in when you collect your data. The important thing here is that in that tabular data section on the left, there's a QC area, and you can turn this on or off. And turning this on is the first thing I would do because it's going to give you real-time information about errors and warnings. Once something happens that's really bad, it will show up in red text, so that's something you need to address in the field. And then everything else that's just some kind of QC will be in black. Yeah?
Is there any way to slow it down or expand it so you can see it? Because sometimes when you're out taking measurements, it's like ripping by and it's a little tiny window and you can't really see what's going on.
No. There isn't a way to do that. In RSQ, you can at least it'll highlight the sample in the color plot as well, so you can at least kind of figure out which one it is. But yeah, no way to currently slow it down. Yeah. Okay, so things you can't fix once you leave the field. Knowledge of a moving bed. So you need to test for that so that you know if one exists or not. Your transducer depth. So so the boat is going to be sitting on the water, and the transducer is sticking out the bottom of the boat. And so the water line is usually about here, and so there's this natural distance from the water line down to the face of the transducers where we're not measuring anything. And that is the transducer depth. And so we always have to enter that. You can enter that afterwards, but you need to know what that is in the field because that space, while you think it might be small, will actually make a big impact on your final discharge. You also need to do a compass calibration. That is critical. Pay attention to your GPS quality. You can't fix your GPS afterwards when you get back to the office. Beam separation. That's another one that you cannot fix in the office, and that one you will be warned about in that QC window. So that's why I always tell people turn that on immediately. Making sure you have sufficient depth. We always need to have at least 2 cells below the instrument so that we can actually fit a velocity curve. And then boat operation, you can't fix that afterwards either. So those are the things you really need to pay attention to when you're collecting data. All right, so I'm going to close this and launch up my simulation here. Okay, so this is RSQ software. And this is the software that you would use to collect data with the RS5. This software can also be used to review data from the RS5, of course, and then also the M9. So we'd start a new measurement, and I'm going to choose moving boat because that's what we're going over today. But if you needed a stationary measurement, that's how you would get to the stationary measurement. So this brings me to the smart page here. And SonTek designs all of our instruments with a smart page so that we can make sure we're getting everything set up before you start data collection. The idea is that you would turn all of these red X's into green check marks. I am showing it, okay. So top section's just instrument information. You can't change that, but it gives you information like firmware, serial number. The test here is not going to run because it's simulated, but it would check battery voltage, temperature sensor, and then also communication with the compass, because all three of those are requirements for a measurement. The next section is your site information. So you fill out as much of this as you possibly can. Beaver Run. It seems annoying to fill this out, but it's worth your time. Because if you have to review the data later, or if you hand data over to anybody else, putting as much information in here will save you a lot of headache in the long run. For vessel, I always indicate what board I'm on, if it's a manned boat, or if I'm on the hydro board, if I'm on the torrent board, if I'm on the remote control boat. I always indicate that because that's going to give me a little bit information when I look at this later. If I had gauge height, I could enter that in here, and then I always put the weather in comments. Wind can definitely impact your data, same with rain, of course. So we'll fill that section out, and now that's a green check mark. The next section here is our compass calibration, which it's not going to let me go through this process, but you can see what the screen would look like here. So this is where you do that dance that I demonstrated, so the 2 rotations. There would be a start button and then a finish button that you'd click after 2 minutes.
I'm sorry, I got a question.
Yeah.
When you do the compass calibration, does it tell you if you're good or not, or does it just kind of like, yeah, you did it, so?
Yeah. So it'll tell you if it passed or not.
Okay.
Yeah, exactly. And if it passed, it'll be in this green background. If it failed, it would be a red background.
Okay.
Yep.
And then you just recalibrate if it fails.
Yep, that's right. And then if it still fails again, then you call tech support. That used to be me, so I could say, call me. Okay, so system configuration here. We're going to enter that transducer depth, so from the water line down to the face of that vertical beam, that the transducers. So we measure that. It's very important to measure it. I'm not going to measure it. Magnetic declination. This is really important when you have a GPS connected. So our RS5 has a magnetic compass inside. That's why we're calibrating the compass. And our GPS is GPS, so it's pointing to true north. So we need our magnetic north and our true north to come together on the same grid. So we enter magnetic declination to take that into account. And I haven't looked it up here yet, so I don't know what it is. But you can look it up on the NOAA web page, and then I have some coworkers that really like the CrowdMag app. So you can look it up. This is something that you can enter later on. So if you don't have it when you make the measurement, just know that you need to make some adjustments afterwards. I'm going to guess.
8.2.
I was way off with 12. 12, my favorite number. Good with that every time. All right. This section is where you would enter your salinity if you were not in a freshwater stream. So if you had any kind of saline input, you'd enter salinity here. There's also some overrides in this section if for some reason your temperature sensor wasn't working, or if you were working in really, really saline environment and you needed to put in a sound speed correction. The bottom half of this is how we're setting up the ADCP for the actual measurement and what we're going to see in real-time data. So our coordinate system is ENU, so that's our Earth coordinate system. That's referencing the magnetic compass. ENU means east, north, and up, and so that's going to allow the ADCP to rotate as we collect the measurement, and it's going to compensate for that rotation. The instrument itself does have an XYZ coordinate system, and there's a positive X arrow on the instrument. If you needed to use those coordinate systems, you could. You just need to keep it oriented. For depth reference, we will choose the vertical beam. We have the option of choosing vertical beam or bottom tracking. So vertical beam is the center beam that's looking straight down. It's just an echo sounder. And then we have the outside velocity beams as backup to our depth reference. So if for some reason vertical beam drops out, we can fill in with bottom tracking. And we'll have access to both of these depth references after we collect the data. So it's collecting all of these different references for choice afterwards. For our track reference, I typically set this for bottom tracking. I tell people if you can bottom track, bottom track. Think of GPS as another tool in your toolbox. So if you encounter a moving bed, that's when you go to GPS. But I always tell people bottom track if you can. So that's where that's what I'll set this as. So these three are going to control how I'm viewing data coming in. So that means my discharge is being calculated based off of bottom track, vertical beam, and ENU. In real time. I can switch all of these around after I collect the data if I need to.
So what a good time-saving thing for you at a site where you know always has a moving bed.
Yeah.
Would just be to always just skip all that, skip the loop method, skip everything else, and just go straight to GPS.
I would definitely set my track reference to GPS here. Skipping the moving bed is dependent on if you have to hand that data over to anyone. Like if you're ever going to hand your data over to the USGS, they're going to require a moving bed test, even if you know there is one and you're going to overcome it with GPS. But if you don't have to give it to anyone, then yeah.
It just documents it in there that yes, there's a moving bed, or no, there's not a moving bed in with the data file.
Yeah, yeah.
So if anybody else is looking at it, they can look without looking at field notes or anything else and say, okay, yeah, there was a loop method done, no moving bed, or there was a loop method done and there isn't.
Yep. All right. So that takes care of that section. The last setting on the smart page is the edge configuration. So if I knew ahead of time what those distances were from the edge of water to the ADCP at each of my edges, I could auto-fill them in here so I don't have to type them as I'm collecting data. But I'll leave these as 0 for now. The one thing that I do want to make sure is on is this auto edge profile. So what this is going to do, it's going to automatically collect 10 samples at each edge, and then when it's done with that, automatically transition me into that center section where I'm moving the boat. So this setting, I prefer it. It saves you a couple clicks, but just wanted to point it out because not everyone knows about it. Also, some people don't realize they have it turned on, and it can trip them up if they don't realize it. Okay, so we'll get into actually making a measurement here. So first thing I'll do is I'll start the system sampling. So I did everything on the smart page. I've now thrown it into the water. It's connected to my tether. We're looking out at this beautiful stream. The birds are chirping. It's fabulous. And now I'll start the system. So it's just pinging right now. We're in what we call preview mode. That's indicated by the sample type here and then also sample type here. So all we're doing at this point is just making sure that everything is working. So we're checking to make sure that our GPS icons up here are live. If I was waiting for RTK, then I would be waiting for this RTK symbol here to go blue. These will be yellow and red before you get locks. And then I'm also making sure that where I have my boat positioned at my edge, that I've got enough cells underneath. So these color rectangles that are populating here, those are all the cells that it's measuring underneath of it. So this looks like a decent spot to start a measurement, and I've got all my icons live. I've got plenty of depth. So at this point, I would either go start my first edge, and I'd need to get that distance, or I'd start my loop test. And I think for the purposes of time, I'll just go into my start edge here. So I'm going to hit start edge. This brings me into my edge dialog box. I have to say what bank I'm on. I'll say I'm on the right bank. And then I need to measure from the edge of water to the center of the ADCP. So I would do that with either a laser rangefinder or a tape measure, and then enter that distance here. So enter that, and then by the time I hit OK, I'm already out of the edge dialog box and I'm in transect. And that'll make a lot more sense when I come back the other way. So at this point, I'm in transect as indicated by my sample type up here. I also know, because my whole entire screen is now taken over by my transect window, my transect tab is highlighted. So that's how I know that I'm in transect. These are simulated data that are being thrown in, so the actual GPS and bottom tracking are not going to line up like they should. So at this point, we would be towing the boat across into that moving section of the stream. I would be looking at my icons up here to make sure none of them turned red. I would be paying attention to my QC window here, which is throwing me all sorts of alarms right now. And then the other thing I'd be paying attention to is my boat to water speed. It's really critical that whoever's operating the software is communicating with their boat operator. You might be doing this on your own, so you might just have this tablet folded. You might have the software running on a tablet that's around your neck, and then you just kind of drop it as you're pulling the boat, say. So whether it's you communicating with yourself, you need to pay attention to boat to water speed. The boat to water speed ratio is automatically defaulted as what we plot at the top time series here. So those are the bar graphs. They're all green right now because our boat to water speed is less than 1. I would be looking to make sure that none of these are red, or if they were starting to show a lot of yellow, then I would be worried that they were starting to go into red. And then the other thing I'd be paying attention to is my SNR plot here. This looks great. They're all kind of trending together. So say I've reached my far edge at this point. It's a really strange looking channel. I'm going to hit end edge. I now need to measure the distance from the edge of water to the center of my transducer. Let's call it 7 feet. You should really measure that. Hit OK. I spent too long in that window, so it automatically popped me out of the edge dialog, and so now I'm in transect again. Sorry, I'm in preview.
That edge of water is the area where you can't measure because it's too shallow.
That's right, yeah, that's right, yeah. So you're getting as close to it as you possibly can before you lose cells. So when I got out of that edge dialog box, it finished up the 10 samples at that edge, and then it ended that transect. So now I'm back in this preview mode. So I can tell I'm in preview mode because of this. And so when I'm ready to start my next edge, I will hit start edge. I've got my 7 feet in there already, so I'll hit OK. So this is what the edge window looks like. You've got your left bank on one side and your right bank on the other, and now I'm in transect. So I'd tell my boat operator, start moving. And then we'd start moving the boat across the transect. I'd be paying attention again to my boat to water speed up here at the top. My QC warnings in here. And then each of these QC warnings that we see over here are associated with one of these squares here, which I'm not going to be able to click on because they keep moving. But it's an easy way to kind of see what the issue is at each of your, if you do get a QC warning. So we're moving across. We've got this really shallow section in the middle of our transect for some reason. And now we are nearing the end edge. So I'll hit end edge. We've got my distance in there, so I'll say okay. So now we're at our edge. We're collecting our 10 samples here, so we're holding the boat stationary. And then once it finishes with the 10 samples, it automatically goes into that preview mode, so I can make any adjustments I need to make before starting my next transect. So at this point, we've collected 2 transects, so we've done just 2 reciprocals, and we would need to collect a lot more if we wanted to follow the USGS SOP. And if you wanted to check to see how long you've been out measuring for, you can do Control S. It'll bring up your summary window, and then your total duration is down here in the total section in the duration column.
So that's once over, once back.
Yep, that's right. Yep.
And how many does USGS require?
So they require a 12-minute exposure time. So if it's a really wide channel like the Mississippi, you only do 2 transects. But in narrow channels, you could be doing 6, 8, 10 transects. So say we did more transects. So in order to close the measurement out here, we do cancel because I don't want to start another transect. And then I would just save and close the measurement. If I decided that, oh, I actually did want to do a loop test, I could do that, or I can do an SMBA test. You can always add those at any point when you're in this, as long as it's any time before saving and closing the measurement. So I'll hit save and close. And that's that. I'll take any questions. I'll throw this up here.
Got one question about the batteries that you put in the boat.
Yeah.
GPS sensors and all that stuff. For some reason, you're having to do a lot of work, and all of a sudden, the batteries are about to die. So if you swap them out fast, do they keep everything, or you got to start from scratch again and recalibrate and everything?
Yeah, so that will end up powering the system off. So you would have to then reconnect, and technically you should redo the compass calibration because a different battery might create a different magnetic field.
Okay, so it's always safe if you change the battery.
Yeah.
Recalibrate.
Yep. Yeah.
Or you get overtime.
Yeah. That's a great way to look at it. Yeah.
Great presentation.
Oh, thanks.
Appreciate it. So having no knowledge of your instrumentation and trying to simplify, how critical is it to have the GPS and the telemetry? Like I'm just envisioning if you have the A5, you have a simple like profile cross section of like 20-foot tag line. You know you're starting at half a foot and ending at 19.5 feet, and you have that Bluetooth connectivity to like a laptop. Is it possible to do a profile and not meeting USGS standards or anything like that, knowing it took you 3 minutes to do the transect? Can it like automatically, like just for estimated stuff, because what we're working with is like for fish passage and stuff, that it's kind of ballpark, not really super critical. Is that like a capability to like simplify instrumentation? Like you don't have to have the known GPS coordinate to start and end if it's
Right. Yeah. And you can make a measurement without GPS. Like you don't have to have the GPS on there. As long as you don't have a moving bed, then it will be able to keep track of where it is, how wide the river is, and it'll be able to calculate that for you. Yeah.
so even with a moving bed.
Yep.
And you do like multiple transects. Like I was saying, if it shows, you know, what the cross section is, the distance, and your start time, end time, wouldn't it normally like automatically divide, like, you know, halfway through your measurement, you're at the middle of the transect?
No, it's not going to do that. You have to. That's just not how it works. Like you're going to have to tell it.
So yeah.
Yeah, I mean, it's not going to be able. It's pretty smart, but it's not that smart to figure that out.
Yeah, and you don't need GPS at all to
Yeah.
make a measurement, and you can make a bottom track measurement and correct it with a loop